I should probably stop eating my apple then.
Only if it's finished. Get all of the goodness that you can. Now you can be finished.
All right. Oh, I had to share my screen. That would be helpful. This would be a difficult class if you could not see my screen. All right. Can everyone see the opening slide here?
Yeah, we can see it.
Yeah.
Nice. All right. So first of all, here's our little quiz that we don't actually do, but if you want your participation extra credit point for the day, can anyone answer this question and give me a little explanation as to why?
It would be D, because in this case, the activation function is the max function rather than a sigmoid or a ReLU or something else.
You sure about that?
Oh, wait.
It's actually B.
Is it B?
Yep. ReLU, remember ReLU is the maximum of 0 and x. In this case...
Oh, is that? Oh, okay.
Yep.
I didn't consider that would look like a ReLU if you graphed it.
Yeah. ReLU is strange, but it's really helpful. But yeah, who am I giving points to?
Are you giving points if I got it wrong?
Sure, why not? I'll give you a point, and then who answered it to?
Karthik, Kartik.
Yep. All right. And Nick, you were the other one who answered?
Yeah.
Cool. Alrighty. So yeah, that's ReLU. That's a 2-layer with ReLU. First, I wanted to show you something kind of neat. This is an entire neural network programmed in 11 lines of code. And 2 of the lines of code are just setting up the x and y. So you can think of this as actually being like 9 lines of code. In this case, we use a lot of the time NumPy. You're going to have to get used to it for the homework or for the lab. But here is a NumPy array. In this case, you can see that it's a 2D array, and it has four records, each containing 3 elements. Y, on the other hand, has just 4 different, one label for each of these. And the way to think about this is the data. 001 would be the data for the first record, and 0 would be the label for that record. So next step here, can anyone guess what this sin 0 and sin 1 are? Any guesses?
Are they the weights?
They are the weights, yeah.
Like sin stands for synapse there.
Yep. It's a sneaky boy. Yeah, that's the weights. In this case, they initialized it randomly with a few extra little modifications, but don't worry about that. And that's the weights we have. And then we do this for loop 60,000 times. In this case, that's epoch. So this is the number of times we're going through our samples here. So first thing we do here is we do our forward pass of our layer 1, forward pass layer 2. We end up getting our delta, just like we had in the slides there. It's merged the layer 2 error and layer 2 delta calculation here, but and you can get these deltas, and then they change the weights by adding to them, adding your dot product of your inputs to each of those layers with the deltas. So this is basically it. This is the whole neural network right here. And with this, it can learn to recognize these different number patterns that it has put in. Is that very useful? Probably not, because it's just these little number patterns, but it's nice to know that we can do that with such a small little script. I mean, this is the whole thing. This is just training an entire neural net here. And again, the only thing we're keeping track of here, like this one doesn't have biases. It's not a complicated network at all. But the only thing we're keeping track of is these two weights. Anyone have a guess as to what activation function we're using here?
The sigmoid?
Very good. Yeah, you can see that right here as we have our sigmoid. So yeah, who was that?
Josh.
Nice. Yeah, so we got our sigmoid, and we'll move on here. So logistics, today we're going to be covering more on the implementation side of neural nets. Yesterday we did, or last Wednesday we did mostly theory. This should help a lot for your lab, which I believe you have a week and a half left-ish. And we can go on here.
By the way, Max, it seems like someone's raised their hand in the chat.
Oh, did they? Let's see. How do I... No. Do it that way.
Oh, yeah, like that.
We had a question, or did we have a question?
I raised my hand. Sorry.
Oh, you're
for
good.
Interruption. So I have a question about the slide with the 11 lines of the neural network. Could you explain why again, and like the second line, and also why the transpose?
Yeah, totally. So which lines were the confusing ones?
Second line.
This one, the y equals NP array.
Again. You should
I
share.
think the screen is off.
Oh.
We can't see your screen.
Gotcha. Here we are. Can you see it now?
Yep.
So which line was that?
Second line.
Okay, so y equals NP array. So those are the labels for our classes. So you could almost think if this could be dog and cat. This could be will pay back the loan or won't pay back the loan. This is the they're the class labels in our classification problem here. This is what we want the neural net to be able to predict. So what we want it to be able to do is see an input of 0, 0, 1 and output 0, and see an input of 1, 1, 1 and output 0. And if it sees an input of 0, 1, 1, it'll output 1, and so on and so on. So that's why we have that there. Does that make sense?
Yeah, and just a quick follow. And why the transpose at the back for the NumPy array?
Oh wow, that guy's racing. So the transpose is just so it fits with our calculations. We're going to be doing dot products in here. So that is, a lot of the time, y is going to look like that. The way you want it to be laid out is such that we have one record, one record, one record, one record, and then the same thing here, except with instead of having all these elements in there, it's just going to be one element per. We could totally have written it out without the transpose, but we would have had to do a lot more actual typing, because we'd have to go and make a different little subarray for each of these boxes, each of these different data units.
A way that I like to visualize it is just like with some like matrix math almost. If you look at X as like each of the three numbers is a row, then you need Y to be a column to do like proper matrix multiplication. If you remember just a bit of like linear algebra, you can't have Y be a horizontal vector. You basically need to have it be a vertical vector, so that 0, 1, 1, 0 are each on a different row, and it just forms its own column.
Wait, wouldn't
That
it
makes
be the other way around, where each of those vectors, or each of those arrays inside of X that array, wouldn't each of those be a column? Because then if you have a 1x4 matrix, that would then be able to multiply.
Not exactly. It's not exactly following the linear algebra example, but it's somewhat. What you want to think of it almost like a database, right? You got your different records going all down this table, and you're going to have, in this case, if you want to do the whole record, like you could combine these together, and you would have 0010 would be the first record, 0111 second record, just by concatenating y at the end. But yeah, it's.
Thank you.
Any other questions on that? This is one that, like, if you're first of all, it's in Python too, so probably you might need to make a few quick changes. But I highly suggest just jotting this down and testing it out yourself and making those changes. Look at the shape of the arrays. You can do x dot shape or something like that, and it'll give you can see what the shape of that array is. So I highly suggest just messing with it a lot. Will help you get a good understanding, especially for the lab, because this is a slightly more simple version of what you're going to be doing in the lab. So can someone mute themselves in there? I think there's shouting in the background. So real quick tangent, I want to talk a bit about pre-processing. How do we numerically represent, when we're putting into our neural net, our different classes or labels if we have categories of data? So let's say we have 10 different breeds of dog, maybe. We have our golden retrievers, our Bernese mountain dogs, whatever. How do we assign numbers to that in a good way? Well, we could just do it the naive approach. We could just say, all right, I'm going to assign one number to each of them. Golden retrievers 1, Labradors 2, German Shepherds 3, so on and so forth. Here's another example of doing that. In this case, we have our different labels here for MNIST. It's a data set of 28 by 28 images, all of which are hand-drawn. And the labels are the numbers they're representing. So in this case, label is 5, label is 0, label is 4. That makes sense. But there's a problem with doing it that way. We don't want the classifier to think that in some way the data is more correlated in some ways. We don't want the classifier to think that the data has to do with what its input is. We'd like it to know what its input is, but we don't want the neural net to have this relationship pre-built into it that a 10 is bigger than a 3 because we assign 10 and 3 as these labels, even though the data that those numbers are representing might have nothing to do with the fact that one's higher and one's lower. So how do we assure that we aren't going to, that we don't have each of these numbers, each of these labels don't have incorrect relationships between each other built in? This is where we get into one-hot encoding, and this is super useful. We'll be using it not super a lot because it's less used for images, but we will use it somewhat, especially for encoding our actual Ys, our actual class labels. So the way you're going to do this, the way you're going to encode your data here, is you're going to take the number of classes you have. In this case, we have 10. And you're going to create an array of all zeros for that, except there's going to be one at one of those locations. So a 5 is going to be here. At the 6th place, we have the 1. 0, the 1's here. 4, the 1's there. And that's how we're going to encode it. We're going to use it as these, code it spatially almost, instead of coding it numerically. Now, that's useful for a number of things, but categories are probably the biggest one. Let's say you have input data. You have, you know that your record is in one of 3 categories. Instead of saying either 1, 2, or 3, what you can do is put in 3 zeros and change one of them to a 1, and that's going to depend on which category it is. Everyone kind of get the intuition behind that and how to do it?
Oh, just another little tidbit, I guess. So another reason, or the way that you could look at this for like the dog example is like previously the problem is that the computer might think that like a Labrador is closer to a Husky than a like German Shepherd or something. So it'll think like, oh, I guess closer than before, even if it gets it wrong. But if we want it to consider any breed that's not the correct one, just as the same level of incorrectness, then we would have to do it this way. Because if you look, if it's 1 and then all zeros, any wrong answer is the same distance from the correct answer. Like if you do like Pythagorean's theorem or something like that, it's equidistant from the correct answer, no matter which wrong answer you choose. So there's no less wrong breed or less wrong category to choose. It's either just wrong or right.
Exactly.
Yeah.
Yeah, that's a very good way of looking at it. These are the basic idea, though. The high-level concept is we want it to be such that there aren't any predefined relationships between these labels. We're just giving it the label and then letting it figure everything else out. So yeah, tangent over, neural nets time. Let's go. How do we implement a neural net? So a couple things we need to consider. What functions are we going to need? Well, we need our activation functions. We're going to need a function that handles prediction, and we're also going to need a function that handles learning, our neural net learning itself. We also need to think about what data we're storing, how we're going to store it, and how we do that in an efficient way, both time and memory efficient. So, first is easy. We can make our activation function pretty quickly here. Here I have 2 of them already defined. Here is ReLU. Fun stuff here. Here's tanh, also good stuff. And you see I defined both the activation function and the derivative of the activation function. But when we talk about that derivative here, it's also interesting to note, you know how ReLU kind of breaks down a little bit because it's not derivable at 0? Well, we just decided to say it's still 0 at that point. Can that make things problematic? Yes. Is it going to ruin our neural network completely? Probably not. In fact, it's still probably worth having ReLU for certain things. But just know for now that this is not 100% mathematically correct, nor is it possible to make it so. Also, sometimes you have like in this case, to implement the derivative, I needed to actually call the original function. In the lab, I believe, you actually don't need to do that because you already have as input the activated version of that. So you can put that X in right away and it'll handle it itself. That's just kind of a pipelining thing more than anything. But just make sure you know what you're actually putting into the function. So what do we store here? Well, the only thing we really need is the weights and the biases. And the way we can probably just treat the bias as an extra weight, one weight each, basically. So yeah, that's fine. Or not one weight, but one input each. So can we store the weights in a more effective way, though? Can we do it more than just like this way where we just have them... I actually don't know what I had the point of this slide for. I don't remember. That's okay. But
I think originally you had a white background and there was some text on it, I think.
oh, I would never use a white background, Sri. You know that. Unless did I? I don't think I did.
I feel like you did it at the very beginning and then switched. I don't know.
But it's not even like you can't see it. It's just a bunch of white dots that seem to be a neural network, but nothing connecting them. Whatever. I'm not going to think about it too hard. I know what this is, and this is how we store our weights. So the best way to do neural networks is through matrix operations. You're going to be... That's why we have NumPy. That's why we were doing that at the beginning, where we had NumPy arrays. Everything can be a nice matrix, and it makes things a lot easier for us, as we'll see in a moment. It lets these calculations go by a lot quicker. And it's not too bad for storage either. It's a good way to keep everything kind of self-contained. The main things we're going to be doing are that we can do kind of efficiently with these matrices, by the way, is dot products. If you remember, when we're doing our original neural network operation, we take our forward pass, we multiply all of our inputs by all of our weights, and then we sum them together. Well, that's just a dot product when you think about it. You're taking two matrices, summing each or multiplying together each of their elements, and then summing them. So that's kind of why we go for this. In this case, I have two weights that are created, weight 1 for layer 1 and weight 2 for layer 2, and they have these nice matrices. You'll also hear sometimes neural network libraries are basically just a combination of a graph library and a matrix library. We can confirm that because we've actually created our own Purdue neural network library. Anthony and Sri will tell you about that at a later date, I think. But I think they can both confirm right now that it's basically just a small graph library and a small matrix library.
Yeah, that's basically all it is.
Yeah. So forward pass. What we need to do is take in... These are more functions, by the way, that we'll have to write. Like, not math functions this time. I know I talk about those a lot, but this time Python functions. We need a forward pass function. This is going to take in an input vector, an output vector for each layer. Every layer in the network, not just the last one. We have a predict function way down here. This is just going to be a wrapper for that forward pass, except we're just returning that last output vector. And the reason we have that is just to make it easy, because forward pass is returning one output per layer. This is just returning the output of the whole neural network. Backprop. This is going to run our backpropagation algorithm we talked about last Wednesday. It'll do a forward pass, and then it'll run a backpropagation. It'll do exactly one, so one epoch, one forward, one back. And then we can have a learn function that just runs a bunch of these backpropagation cycles. So we can make these from scratch, and in fact, in your lab, you're going to be doing that for part of the lab. But there's also a whole bunch of different libraries available for neural nets. One is TensorFlow. Important definitions. A tensor is a generalization of vectors and matrices to higher dimensions. If you have your square and you have your cube, tensor is your hypercube. And it's pretty great because you can use it for any number of dimensions. It does the job. And then flow is the action or fact of moving along in a steady continuous stream. So the basic idea of this library is we have our tensors, our little data packets that are in the shape of matrices or higher dimension versions of those. And it flows them through something, specifically a computation graph. So TensorFlow at its core is a numerical computation and machine learning library. It lets you build these graphs of operations and flow data tensors through them to get output. We can use these graphs as neural nets, and they're mainly used as neural nets, but you could technically do all sorts of stuff with this. You can do even non-machine learning stuff with TensorFlow. And our tensors in this case are going to include our inputs, our outputs, and even our weights. Here's kind of a look at this data flow graph, and you might notice if you ever took compilers, this looks a lot like an AST, and that's basically what it is. We have our variables in here, x, y, and c, and we have a constant here. This means if I introduce x and y to this, we can calculate c very easily, just by running through the data flow. And that's, you basically build neural nets out of that. And they have a lot of pre-built stuff for you, so you're not going to be working directly with a lot of these operations, but they have like layers already introduced. And here's some of those important parts that they give you access to. tf.graph is just their implementation of the data flow graph. You have operations that describe calculations that consume and produce tensors in that graph. Tensor, of course, these are going to be the edges and will be our storage for our data that goes through. And then we have sessions. A session is basically our graph that we are running right now. A graph itself could just be the architecture itself not running anything. The session is what we are running on that graph at the moment. If that's a little bit confusing, just hang in there for the moment. We won't actually be using too much of TensorFlow's non-Keras functionality, but it's worth knowing. First of all, let's take a look at this here. Here I create, and let me check the time. Yeah. Here I create two variables. A is a constant of 3. B is a constant of 4. They both have types. Implicitly, it's just going to be float 32. Then I take total, this object, and I say total equals A plus B, and I print everything. However, it's not, because we didn't do a session or anything, the outputs are not actually 3, 4, and 7, right? Instead, we have these objects that are just representing things that are there. A constant, another constant, and an add operation, which is that total. So if we want to run this, we have to do a little bit more. Here's that graph it generates, though. You see, while we don't have that answer, we do have this nice graph. Here, I actually run that graph. So in this case, I still created A and B in total. But I took session, created a new one, and I said ses.run total. Total being the variable that I want the answer to. It returns that, and there we go. We can print it, and we get that 7. So that's how you run one of these graphs, is you can use that ses.run, create a new session, ses.run your graph that you've created, and you're good to go. Yeah. However, we can do a little bit more than that, too. In this case, what if I would like A and B, what if I'd like the outputs to output A and B also. I want multiple outputs is what I'm saying. Well, any of these variables, I can still do that too. All I need to do is create an output dictionary, and inside of that put the these keys for it, which can be anything. You can rename these however. And put those objects in there, those objects that are making up those variables in the graph. And then it will output that for you, and we can get multiple outputs in case we wanted. It doesn't make much sense in this case because those are just constants, but it could be anything. Then let's say we don't want it to just be constants. What if we want to put data in? In this case, I have x equals tf.placeholder tf.float32. Very similar to a constant, except obviously it's not a constant. It's going to have data put into it. In this case, the only difference is when we do our ses.run, we're going to need to give it a feed dictionary. And this is going to be where we set values to those objects, using the objects themselves as keys and the values of the objects as the values of the feed dictionary. And doing that, we can get the results for this, in this case 3 plus 4.5, or even, and you can see here how TensorFlow is useful because we have these tensors instead of anything else. We put in this list. In this list, we run it through, and it adds 1 and 2 to get 3, and 3 and 4 to get 7. Does everyone understand that, first of all? I can't stop for too long because I do need to wrap this up at the normal time in 20 minutes, but cool. I'll assume we're good then. So we can make one of these pretty quickly. In this case, that was the one we showed earlier, and here's what we get by creating it. We have our constant that will be 12. We have our inputs, x and y, and we have these liminal nodes here to represent this liminal node here for that multiplication, and we can get that c then. We put in our feed dictionary, and we get our answer. A few other useful things. TensorFlow is huge, really big library. If you want to get into the weeds on it, you'll have to just kind of look through it for a while, look at tutorials, all that. But these are the most useful things you'll need to look for. These, you got some loss functions, a dense layer, that's just a normal fully connected layer. Reshape, that's going to change the shape of your tensor in some way. Variable, that is going to be kind of like a placeholder, but it exists outside of a session. And Atom Optimizer, which will, that's the great thing here. You don't have to program backprop here. It can handle that entire thing for you. And that's what Atom Optimizer does. It is doing a variant of that optimization that you've done your backpropagation with gradient descent. So a couple pros and cons about TensorFlow. Pros include it has Keras built in, the data graphs are efficient, it's really good for running on GPUs and stuff, widely used in the industry, and it's open source, which is great. The bad news is it's super low level compared to other neural network libraries, and it's not easy to learn. It's a pain in the butt, which is why we're not going to be learning it too much. But it's worth to know what we're going to be using because it's built on top of this. And that's Keras. So Keras is the main library we're going to be leveraging for this course. It's a high-level neural net library. It can actually run on top of any of these common neural net libraries. CNTK is a big one. Theano is big. TensorFlow is the biggest of the three, though. And it's also the official high-level API of TensorFlow. So if you have TensorFlow installed, you already have Keras installed. You can actually import Keras from TensorFlow as well. In this case, I'm not going to go over too much the underneath details because most of them are just the same as TensorFlow using TensorFlow. So let's just write some code, and you can see kind of how this works. So first thing I'm going to do here, I want to build this neural net. I want it to be one layer. I want the in shape to be this in shape constant and the out shape to be this out shape constant. So I'm going to take this Keras.sequential. That's going to be our main neural net here. We put that into model. And right now it's empty. Right now it's just an empty neural net. We're going to define what loss we're using. In this case, I chose categorical cross entropy. You can read a little bit more about that if you want, but it's good for different categories. Optimization, we're going to use our atom optimizer. Again, I talked about that. That is just an extension of what you normally do with gradient descent. And then we're going to just go ahead and add these different layers to the network. In this case, we're just adding one. We have our in shape here that we have as this tuple, and we say model.add keras.layers.dense. We give it that input shape. We say what activation we want. In this case, I'm using something called a softmax activation. And after that, we compile it. And I think, we go through it actually. So loss, optimizer, dense function or dense layer with softmax, and then we compile and return our model. So that's how we create a full neural network in Keras. We can then train it, which is really easy because we have this nice model.fit function here. It comes with sequential. All we have to say is give it our x, our data, give it our y, our class labels, and tell it the number of epochs we want it to train for. And then we're done. That does the entire training process, all that backpropagation, all that for us. If we want to predict something without doing learning, if we want to just get some information out of it, we can just give it that x, put it into model.predict, and it will give us our predictions. So yeah, Keras is really easy. It's not difficult at all to learn how to use it, and it's also not difficult at all to get to the more complicated parts of it, things like convolutional neural nets. But it's worth knowing that it's just TensorFlow under the hood. It's still using that Dataflow graph and the sessions and all of that. It's just doing it in a more programmer-friendly way. So beyond that, though, these libraries and the TensorFlow at the same time, it's just using these Dataflow graphs to make the operations a little easier, to make the interactions more straightforward when we're making our neural nets. So these libraries are just the same as using those NumPy arrays with our backprop and our feedforward. They're cleaner, they're easier, they're often a lot more efficient, but at the base level here, all of this stuff is the same kind of thing that we've been doing with that backpropagation algorithm and feedforward. This is all just building on top of that. And to close things out for the day, I wanted to one-up that code we had at the start. That code was using just NumPy, but it needed 11 lines. I can do the same thing in 7. In this case, I'm going to import TensorFlow, STF. I'm going to load MNIST. And by the way, I'm not even doing it with some weird little 0-1 relationships. I'm doing it with the full, those numbers, those handwritten digits. Load that in. I have training data, testing data, or training and testing data, and the X's and the Y's. I'm going to do some pre-processing here. I bring them down from being 255 per pixel to just being between 0 and 1. That makes it much easier for the neural networks to figure out. I create my model by saying tf.keras.models.sequential, and then I have I flatten these down because they're images. They're not just one big line of data, so I'd like them to be, though, into 512. That's our first layer. They go into that. They're actually not 512. They're like 700 something. But 512 is our first layer of neurons. We use a ReLU activation. And then we have our output. And we're going to have 10 outputs because 10 different classes. And we'll use our softmax activation again. And that will hopefully give us our answer once we do our fitting. And it did. This was our output from that. We ended up with an accuracy of 97%. It's kind of covering up there now, but yeah. Just from the 7-line little thing, we got 97% with Keras. So that's all I have for you today. Next week, we are going to be doing a little bit more, so we might go overtime that day, but today we won't. And then later today, I'm going to, again, have a quick little session you can drop in on. We can talk about the homework or the lab, however. It'll probably be around either 7 or 7:30. Again, I'll post the specific time on Piazza when that happens. TAs, you are very much invited, but if you can't go, I know it's last minute, that's fine too. And that's all I have to say. Any questions?
I just wanted to make a note that on the Piazza, I should be making a post this week about office hours starting next week. They might just intersect with my 252 office hours, or maybe just like an hour or two beforehand. But I'm still figuring that out. But just I'll keep you guys posted on Piazza regarding my office hours for 390.
Good stuff. Yeah, I also have office hours, the same ones as the 252, so you can try to go in and they've been in high demand lately with the time slot, so be careful to get in early for those. But yeah, that's all I have to say for today. Yeah, see you later. Good luck on the lab, and don't stress too much on the homework. Definitely get it in by today, but don't stress too much on getting it exact. It's not a huge deal. It's mostly just that you're understanding the concepts. All right, peace.
All right. A quick question.
Oh, yep.
The homework. How much work do you want us to show on that?
You don't have
Because,
to.
sorry.
Yeah, you're good. You don't need to do the calculus as much. You can if you want, but mostly just show me the forward pass at the very least.
Okay.
Yeah.
I have that on mine.
Yeah.
I was just making sure that the one that I turned in, I didn't need to scan this mess.
Yeah, you don't
need.
You don't need to do like the whole matrix operations and everything once you get to the back prop. It's just give me broad strokes as to what you did.
Okay.
All right. Well, any other questions?
Yeah, quick follow-up. Can we submit handwritten work?
As long
Is
as it
handwritten
is
fine?
as long as it is readable and in a PDF form,
Yeah.
like you scan it, that's fine.
Okay, thank you.
Yeah. All right, I think that's it then. See you later, guys. Peace.
All right. See you.
See you.